Okay, well, I can see we've got a really good turnout today, so welcome to everybody. It's my pleasure, an honour to introduce tonight's speaker, who is Don Dingwell. And Don, we were just, you may have been hearing, we were just chatting about his interests in volcanology. He's one of the world's leading volcanologists and renowned for his experimental approach to studying the physical properties of volcanic systems. But as we were chatting, it became obvious that volcanoes raise all sorts of exciting interdisciplinary issues and thoughts, which I'm sure we will probe this evening. But to give you a little bit of background about Don, via a PhD in geology at the University of Alberta and a Carnegie Research Fellowship at the Geophysical Laboratory of the Carnegie Institution of Washington, he eventually landed up in Germany as assistant to the director of a newly founded research institute. And then in 2000, he was awarded a chair in mineralogy and petrology at the Ludwig Maximilian University in Munich, where he founded and now directs the Department of Earth and Environmental Sciences. Don's principal interest, research-wise, is in the physico-chemical description of molten rocks and their impact on volcanic systems. He's contributed largely to the development of the new and expanding field of experimental volcanology. He's incredibly productive and influential as a scientist, having published around 450 papers. He's got more citations than you can shake a stick at. His outstanding research has earned him many honours and recognition by numerous scientific awards, again, more numerous literally than we have time to mention individually. He's an elected member of several national academies and has had a number of honorary degrees bestowed and visiting professorships at prestigious universities around the world. Indeed, apparently the President of Germany herself has bestowed upon him the Order of Merit of the Federal Republic of Germany, and the Governor General of Canada has recently announced his induction as an officer into the Order of Canada. So tonight's speaker is extremely distinguished indeed. He was also, I should mention, the third Secretary General of the European Research Council. Now, during his time and his fellowship at the IAS at Durham, Don's interacting with colleagues using innovative methods to study the properties and behaviour of magmatic systems to enhance our ability to forecast and cope with eruptive events and their short and long-term impacts on the Earth system. And I was fascinated to hear from Don just now about various sort of serendipitous outgrowths of the project that are emerging. But tonight, he's going to speak to us about volcanism, from wonder and fear to experiment and intervention. Over to you, Don.
Thanks very much. So what I've prepared is about 45 or 50 minutes, I think, of a recorded Zoom lecture. I'll repeat a few comments about where I am and where I come from. I find they're quite useful to understand what one is saying. And I recently had to do it in China, so I'll repeat it here for you, what I did for them. Yes, you'll see what I'm about to talk about is primarily experimental, and it's very unusual in earth sciences. They're not dominated by experiments, never have been. But of course, the right experiment can cast an enormous shadow in a positive sense on the interpretation of geological events. So without any further ado, I'd ask Rowan to start the video, and I look forward to speaking with you again at the end.
I've entitled today's presentation, Volcanism, from Wonder and Fear to Experiment and Intervention. I hope there'll be something in it for everybody, and I've tried to really encompass the span of fascination and the wonderment that leads us to investigate these objects all the way down to the very bold suggestions that we have to make at the end of this presentation about intervention. Just a word or two about myself. I think the host very much for the introduction. I'm originally from this part of the world where there aren't a lot of volcanoes. In fact, it's a fairly cold place, the east coast of Newfoundland. I got my first degree there at the Memorial University of Newfoundland. And then I did my PhD about several thousand kilometers to the west in a place called Alberta, which was a very different geography, a very different economics, and a substantially different culture, even within Canada. I went for my first and only postdoc to the geophysical lab at the Carnegie Institution of Washington. This gentleman pictured on the left is born in this country, not too far from here. And of course, the most famous son, if you will, of the experimental investigations of earth sciences, which began at this place about 120 years ago, is this Canadian gentleman on the right. His name is Norman Levi Bowen, a father to all of us who venture into the lab to understand rocks. In 1986, I was headhunted away to Germany, to a very small town called Bayreuth. I really didn't know anything about Bayreuth except its location on the map. And there we built what rapidly became, well, within a decade, one of the most highly respected experimental institutes in geoscience in the world. And that was what was the draw to bring me away from an assistant professorship at the University of Toronto in the mid-1980s. And in 2000, I received the call to come to Munich. There's pictures of the University of Munich to take the chair of mineralogy, petrology, and to start a new department a few years later called Earth and Environmental Sciences, which I've chaired to this day. Our group works very intensively in research and in projects and in infrastructure. I just put this slide up because it conveniently captures at least 5 of the most important granting agencies that we have for our work. The German Science Foundation, the DFG, the University of Munich itself, LMU, which has very generously over the last 20 years supported my existence there. The European Research Council, where we've been lucky enough to receive 2 advanced grants. The Volkswagen Stiftung Foundation, where we received a grant regarding the impact of ash in the Earth system. And the Center of Advanced Studies at the bottom right, which is essentially the Munich equivalent of this Institute of Advanced Studies at Durham. Volcanoes sound very exotic to many, a little less exotic to all of us since the Eyjafjallajökull eruption about 10 years ago in Iceland. The UK received more impact from that than I did when I was sitting in Munich, but even Munich airport was closed. So that is something that certainly thrust volcanoes into our center. This has happened throughout prehistory, throughout history of mankind. And I just thrown up a few provocative pictures here to remind me, say that to you. If you look on the right-hand side of the diagram, you can see footprints from the East African Rift Valley, which have been laid down in what is postulated to be volcanic ash, which has been lithified. So you can imagine these hominids walking through a pre-modern environment, an environment in which the ash is now slowly turning to sediment, and they're walking through the wet sediments at this time at a lake bottom. If you look to the center, you can see the perhaps somewhat controversial description or translation of a mural which is found in Çatalhöyük in central Anatolia. It's been estimated to be about 9,500 years old. It has been postulated to represent the eruption of a volcano, which you won't find difficult to imagine looking at it, above the multiple dwelling settlement, which was the village which was in the area at that time. Fascinating to speculate on somebody that might have thought it important enough to draw a picture of what might have been an eruption going on at the time. And if you look to the left, you can see something which you can clearly place in Central America. And what you see here is, of course, in this beautiful rectilinear form of the ancient Mexicans, if I could be non-anthropological about it, demonstrating a volcanic eruption in prehistory there. So it's something which has continuously impacted our ascent, both in a anthropological sense, in a physical anthropological sense, but also in a historical sense. And to underline that perhaps a little bit more, we jump to the recent events of history and one or two of prehistory. If we can start at the top with Krakatau, which erupted in 1883, and due to undersea cables in existence at that time, the information was sent around the world. It was, if you will, the first globally well-known eruption, which reached Europe. People were sitting in Britain making measurements of air pressure and actually received information on the pressure waves which were sent around the globe due to the explosion at Krakatau, a half of a world away. We have 1815, Tambora, Sumbawa. It's worth looking at where that is on the map. It's also about as far away as you can get from us as is possible. But it is something which impacted directly on America and Europe in a climatological sense. We had the so-called year without summer in 1816. It's been speculated that the Battle of Waterloo was taking place under extraordinary conditions of weather, and that this may have had some influence in the whole matter. Certainly, we had famine in Europe. We have drawings, woodcuts, and so on, which describe this to us. We also know that the agricultural college, which became the University of Hohenheim, was set up at this time in order to understand a little more about what affected agriculture initially. And it's been claimed that the bicycle was invented about this time because of the number of horses which died across Europe. Lucky Iceland, 1784. I don't need to go into any depth on the date. Lucky was in activity at the time of the food famines and the riots and all of the events which led on, immediately up to the political responses which were inadequate, and thereby eventually the French Revolution and the beginning of the modern, causing convulsions and waves of emigration after the reign of Napoleon and driving large numbers of people to go to America for various reasons. 1453, another date you'll all know from your history, the fall of Constantinople. It's been speculated that again in this year there was bizarre weather in Europe, and that there have been candidates proposed for volcanic eruptions that might have been capable of dropping European temperatures 1, 2, maybe 3 degrees Celsius, enough to have drastic impact on the subsistence of the population of Europe, based virtually entirely on agriculture. I won't go any further. The other dates you can speculate upon. I'll mention 1620 before Christ, Tira, Santorini, explosions there, which probably sent tsunamis to the north coast of Crete. Can we infer that the eventual collapse of the Minoan civilization, with all of the impact that that had for the civilizations that came in its wake, might have been influenced as well by tsunamis associated with this eruption? It's quite possible. Tsunami deposits have been found on the north coast of Crete. And finally, 75,000 years ago, Toba, Sumatra, the largest explosive eruption that we know of in times of modern humanity, of Homo sapiens, if you will, and of course also Neanderthals at that time. And you may know that we have the issue of the genetic bottleneck, that you and I and everybody else in this room are much too closely related to each other, considering the length of time that the human species has been on this planet. And it's been speculated that we had a near extinction event around 75,000 years. Who knows? The magnitude of what we've seen in historical time with volcanic eruptions is very, very small. Here you have a series of half a dozen eruptions. And if you look to 1980, which many people in this room will have experienced, you know that it had a big impact scientifically in the United States. By pure fortune, it did not have a big impact in terms of loss of life and loss of infrastructure, because it was a directed blast to a relatively uninhabited quadrant to the northeast. Had it erupted in 180 degrees in the other direction, it would have probably wiped out the city of Portland, Oregon. Nevertheless, it was a very, very, very small eruption, as you can see by this comparison. Pinatubo, which many of us will also have in memory from 1991, which led to curious weather for a couple of years afterwards over Europe, drops in temperature, was also a relatively small eruption, although it caused, of course, massive impact in the Philippines where it occurred, including the shutting down of US bases and many other actions. There you have Krakatoa, we've just referred to, Tambora, we've just referred to, which clearly had a global climatic impact or climatological impact, yet is moderate in size. And if you look then to the last two cubes in front of you, you have Long Valley Caldera and its eruption 760,000 years ago. You have Yellowstone and its eruption about 2 million years ago. And you have Toba with this 75,000-year-old eruption. The scar of Toba is very clear to see. If you Google Earth Sumatra, you very quickly see an oval-shaped lake in it. That is the hole in the ground where Toba came out 75,000 years ago. I've already presented you in my brief talk a few weeks ago with this simplification of the notions that we're dealing with here. We try to put eruptions in the context of the entire Earth system sciences and look at it as a communication between the state of the upper lithosphere and the impact that an expulsion of material from that can have in the atmosphere, the hydrosphere, the biosphere, and of course, as I stressed last time, also in the technosphere, which you can also call the anthroposphere if you want to. These things are man-made. There are many spheres which we can describe in the Earth system. And of course, we describe them purely for the purpose that is at hand. So volcanism, it's happening actually all around us all the time. Here you have, for me, is a beautiful phreatomagmatic explosion. Add water is a bad piece of advice for volcanic eruptions. If we add water to them, they tend to become even more explosive. And here you can see a striking example of a relatively small volume of material, but a very high degree of ballistic ejecta energy. You get the impression here that you have a still shot of something which is moving very fast, and that's correct. Magma and water don't mix well. These eruptions generate rafts of pumice. If they are in the ocean, these pumice rafts are composed of highly vesicular or highly porous material. And this highly porous material gives it the buoyancy that it can stay on the ocean surface and transport actually anything that is willing to jump on the pumice raft from one landmass to the next, as you can imagine, might be occurring right here from the left, where it originates, to the right, where there is another island. So if you speculate about species and invasion of species from one landmass to another, quite possible that oceanic pumice rafts play a role between the islands. Of course, here you go. It's a beautiful example of the intersection between technology and pumice rafting. This ship, presumably a warship, is not driving into this pumice raft. It's very carefully edged up to the side of it. It does not want to go through this pumice raft because this pumice raft will have the effect of scouring, scrubbing, taking the paint off, etching, and perhaps even more, the exterior of this surface ship. So pumice is something which is great if you want to remove things from technology, but if you don't, then you want to avoid it at all costs. The problem is global, as I've already said. You literally have volcanoes on the other side of the globe erupting, which impact us directly. But of course, there is also the acute problem and the immediate problem of at least 500 million people. These statistics are now a decade old, of 500 million people who live less than 100 kilometers from a Holocene volcano. Many of these people live on islands, which means they absolutely are restricted from rapid evacuation in the case of a catastrophic event. And you just have to look to the northwest of this country and speculate on Iceland and realize that this is a country which, from a single volcanic eruption, could have impact which influences the entire population there. The ways in which these volcanoes are problematic for us are many, and it's truly striking when you try to count up the possibilities. And each color on this pie diagram represents a different cause of death associated with volcanism. And many of them are not the things that you would normally think of. You're generally, for example,
not attacked by a lava flow. These things usually flow in a predictable manner, but you can be killed if you do something foolish or unfortunate in the vicinity of one. You can be asphyxiated by the gases. You can be buried by avalanches. You can be drowned by tsunamis, and so on and so forth. This is just here to point out to you that the civil protection issues associated with volcanic eruptions are very, very complex. And there are more than a dozen different main challenges, multi-hazards, which are associated with these events. Now, I'm a physical scientist, as many of you know, have seen in the last presentation or have inferred today. What we try to do is get a simplified picture of a volcano. This is a child's drawing of a volcano in an exercise that we did at the university. And you can see that the list of topics or the list of approaches on the left-hand side is an attempt on my part to break up the modern field of volcanology into the kinds of studies that we are doing and which are complementary to each other and hand in hand should allow us to validate each other's approaches to what we can say and what we know we cannot say about volcanic processes. And there are three key words. The first word on the top is field. The second word, or the first word in the second category is theoretical, and the first word in the third category is laboratory. So you immediately get the picture, all the elements of a modern science. The classical field, over 100 years old, of physical volcanology, which has produced exquisite works of detailed observation and interpretation, is the field of volcanology. That's what 95% of volcanologists are, conservatively speaking. But added to that, of course, is the field-based, relatively high-tech business of monitoring of volcanoes. And that's where all the money goes in volcanology, simply put. The geophysical, geochemical monitoring of volcanoes, and as we'll see in a minute, also geodetic monitoring of volcanoes. The models are theoretical in nature, but of course numerical in their application. There are approaches to analytical models for things such as lava flow in a tube or in a chamber, but there are also numerical modeling techniques which basically dominate what we can say based on a algebraic expression of all of the factors that we believe we need to describe lava, magma, ash, and all the participants in the volcanic system. And the third category is really the poor cousin of all of it. It's what I do. It's what I represent to most of my colleagues in volcanology. There's probably about 100 of us around the globe, but we survive because what we do is actually quite useful when it works well. And that is we put the numbers in. We put in parameterization of the materials that are in the system. And we also put in observations, some expected, some planned, some unplanned, which show us what magma is capable of doing if we manipulate it under high pressure and high temperature. Here is a very primitive cartoon showing you the kinds of observations which consume the biggest budgets of volcanic research. This is the monitoring business. And as you can see, you have in the upper left satellite monitoring of the surface of the planet, also of the geochemistry of those plumes coming out of the planet. We have seismicity, which is the predominant, I would say, observational technique which is used geophysically for volcanic tremor. Basically, these volcanics make noise, and we can listen to them by listening to the acoustic energy they release through seismicity. We have also gas measurements. This is the classic way of determining the variations, if there are any, in the plumbing system of the volcano, because volcanoes are degassing everywhere, 24 hours, 7 days a week. They never stop degassing. And therefore, the gas variations, or the variations in the proportions of gases, if we can establish a pattern of them related to actual eruptions, can tell us something which we can use as a diagnostic or as a symptomatic example of what is about to occur. Even groundwater and hydrology and observing changes in chemistry of water and observing changes in water pressure and flow rates from hydro systems, from aquifer systems around the volcano can be used to interpret, to make statements about volcanic deformation. And basically, we observe things continuously on volcanoes. We have what we think is a baseline, in some volcanoes better, in some volcanoes worse. We have an eruptive history, in some volcanoes more frequent, in some volcanoes less frequent. But for the volcanoes where we have very frequent eruptions and where we have a good baseline over time, such as Etna or Hawaii, we have an excellent chance to see when things change, when you go out of that boundary of what you expect is the standard deviation of behavior in quiescence, as we call it, and you move into something above or below, which would imply volcanic unrest. And civil protection basically comes down to the management, or a large part of it comes down to the management of volcanic unrest, because that's something you can do something about. If you interpret unrest correctly, you can forecast eruptions and you can act on time to evacuate people, to make infrastructure decisions, and so on. And this is the plot that I showed you last time. This is my one German plot, just to remind us all to give thanks to that culture for having provided all the money for my research over the last 20 years. We see these systems in a simplified way. We must do that in order to create intelligent experiments. Sophisticated experiments are not experiments which have sophisticated technology. Sophisticated experiments are experiments where there is a clarity of interpretation due to the sophistication of the thinking which has gone in to the design of the experiment. And a fundamental element of this is to break the system down into the fundamental processes, which we then isolate in the laboratory, fully quantify in the laboratory, and after we have quantified them, then we can put them back together in what we believe to be a reliable way with controllable feedbacks, such that we have a series of processes which we can investigate. And here we have, as I've said to you before, the smaller group, the saturation, the nucleation, the growth of bubbles, the foaming of the system, which means we drive this bubbly liquid into a temporary rigid material, to the fragmentation, the production of volcanic ash by breaking the rock in a brittle manner. Most people think of volcanism as something which is hot. You have the hot lava coming down the mountain. Surely temperature is the problem. Surely temperature is the hazard. Well, it turns out that volcanoes are hot, but it is not temperature which is the fundamental challenge to volcanic hazards. I just showed this plot as a demonstration. This is in Goma in eastern Congo in Central Africa. And what you can see is a young boy walking away from an active lava flow which has now dissected or bisected the city of Goma. And this is typically the story with lava flows. Unless you do something very silly, lava flows are something that you can avoid the lethality of. No, the big problem with volcanoes is not temperature. The big problem with volcanoes is the other thing, pressure. These volcanoes are under pressure, great pressure at depth. And as we can see in this before and after picture of Mount St. Helens, you can easily arrive at the situation where you have a very rapid decompression of what was inside of that mountain and snow covered at the beginning and what was expelled from that volcano and is missing now at the end. In other words, by removing a load at the top of the volcano or by changing the stresses in a relatively rapid way through a range of possibilities that influence the stress field on the magma, we have the possibility of driving the magma into a rapid decompression. And this rapid decompression will be one which we may not be able to respond to by viscous flow. Rather, we have to accept the failure of the material. Just to show you how viscous these magmas could be, this is the dome of Chaiten volcano in Chile, southern Chile, several years ago. And this dome is actually creeping like a glacier, slowly. It's still fluid, but it has an enormous viscosity. It has a viscosity near what we call the glass transition, so that on a short time, it stands as a solid, but if you give it enough time and maintain its temperature, it will eventually flow. And this is a tortuous state of matter to be in, because you're constantly faced with the challenge of, do I flow or do I fail? And this is why we've called this the volcanic dilemma, flow or blow, because almost all high silica explosive volcanoes have a choice. They can either relax their stresses if they have enough time at high temperature and produce high viscosity lava flows or domes like you see here, or these events produced can actually explode and disintegrate into volcanic ash, which you find distributed up to globally around these volcanoes. And when these highly viscous lavas do disintegrate, do fragment, they produce the deadliest of all proximal volcanic hazards, the so-called pyroclastic flow, the one you cannot escape. You just have to have the good fortune to be in the right place by the time you can observe it. And what you see here is a pyroclastic flow coming down the side of Mount Unsen in Kyushu in the early 90s. And you can see here the houses for scale. And this pyroclastic flow is coming down on a speed of hundreds of kilometers per hour and at a temperature which is several hundred degrees Celsius. No escape. So we've spent some time at the beginning of my career thinking about what does it mean that these volcanoes sometimes flow and sometimes explode. And we managed to decipher what the trigger or the mechanism is in a material sense for these systems by appealing to the major phase, which lava is composed of, and that is the liquid phase. That doesn't surprise you. You know that these lavas are liquid when you see them on the surface flowing in a river-like manner, classic liquid behavior. But these liquids are relatively viscous. They're not the liquid viscosities that you see in water or things like that. They're several orders of magnitude larger. And they become more and more viscous as temperature decreases. So you can see here time scale from fast to slow for deformation processes, strain rates, if you will. And you can see on the bottom reciprocal temperature, so hot on the left and cold on the right. And you can see then that if I raise the temperature, then I can raise the fraction of the brown curve, which is occupying the diagram. But if I drop the temperature, I can increase the fraction of the gray part, which is on the diagram. And simply put, brown is a liquid and gray is a solid. In this case, a glassy solid. And if you drive yourself into the regime of glass-like behavior, which is solid-like behavior, then you will produce an explosion in the volcano. And this is what the products of explosions in volcanoes look like. I think I've already shown you this slide last time. This is a shot from an SEM, scanning electron microscope, where you can see the tortuous but intricate or beautiful geometries that individual ash fragments can contain, with bubbles which have been drawn out here in a toffee-like fashion to tubes. And down here you can see with transmitted light, which shows you the individual phases due to the optical properties that they have, something with a regular interior, which represents clearly a crystal, a single crystal, and something with a shattered, broken, irregular outline and no interior structure, which represents the glass. Now, the nature of these liquids, as I said, is one of highly variable viscosity. Many elements influence the viscosity. Second to none in that aspect is the influence of water. And at depth, these systems have a lot of water. You get weight percents of water dissolved into these magmatic liquids. And as you drive towards the surface, you drive the water out due to the relaxation of the pressure. And at the surface, almost zero water is able to be dissolved. It melts. And as you can see, there's a kick up in this property, the viscosity, as I drive towards the surface of the Earth. And it is this kick up in viscosity which enhances the explosivity of these systems, because higher viscosity means more likely to behave in an explosive fashion. The decompression rates which the system experiences on ascent to the surface also play a critical role in how these materials behave. Normally in geology, we talk about what we call a lithostatic pressure. It is simply a pile of rocks. As you go down in the earth, you have more and more and more rock above you, and you have a higher density as a result, and a higher ambient pressure. But if I have a flowing system, then it is no longer a lithostatic system, it's a dynamic pressure. And the dynamic pressure and its gradient is defined by the viscosity gradient in the liquid. Because the viscosity generates flow based upon stress, and volume stress is one of the stresses you can think of simply as pressure. And what you can see is you come to a catastrophic drop in pressure versus height. And if that's a constant ascent rate, then that's a catastrophic drop in pressure versus time. And this pressure versus time is the decompression rate. So this catastrophic decompression, which we expect from the material properties that we've seen here in the previous diagram, that catastrophic decompression is what leads to, as a rule, fragmentation of highly silicic, highly viscous liquids. Now, I've said a few words about materials, and of course you get the sinking feeling that I'm going to end up talking about material science, because it's very true. I have to quickly sweep through a couple of things that we do to give you a feeling for what it is like to stand in our labs. It's always important to see how people work in order to understand what I can make of their results. We're building a new building in Munich, and one of the main features we're going to have is accessibility of the public to see how the labs work, so that they can understand how Earth scientists can say what they do say about our planet. You can see here on the left-hand side a so-called low-viscosity concentric cylinder device. It's the kind of thing you would use to measure the viscosity of a glass melt in a glass bottling plant. On the right, you can see something called a dilatometer, which is also used to measure viscosity. But the samples are so viscous that I cannot do major deformation as on the left. I can only do microscopic deformation by penetrating bodies into the body of the liquid sample itself. But using these two kinds of devices from two very different worlds of investigation, we can obtain values for the temperature dependence of viscosity of magmas. And here you have the log of the viscosity plotted as a function of the reciprocal temperature. So we're talking about temperatures up here of about 1300 degrees Celsius. And we're talking about temperatures down here of about 800 degrees Celsius. And this is a range that we have for magmas near the surface of the Earth. And for each color of a curve, there is a dot which represents the composition in terms of total alkalis, sodium plus potassium. These are the two major alkalis, natural melts, and silica, which is a critical thing in determining the actual values of viscosity. And you can see that this is a logarithmic scale of many, many log units, so that at a given temperature, changes in the chemical composition of the natural lavas produce changes in viscosity, which I can estimate here quickly to be from 10 to the minus 1 to 10 to the 8. 9 log units of viscosity at a constant temperature within the bounds of what the Earth throws at us, if I could use that expression. So if you've ever wondered why volcanoes appear to be relatively complex in their behavior, if you've come to that conclusion from observations that you've made over your life, newscasts and so on, you can understand why that's the case if you consider how complex the chemistry is, and therefore how wide a range the properties which control their eruptive behavior exhibits. Now I'm going to bring you on 2 tours across the glass transition. I did one last time, and I did it very quickly. I'm going to give you a little more science now. First, we'll go across fast, and then we'll go across slow. This critical yellow band being the glass transition, which you must cross in order to explode a volcano. So the fast tour begins with this gentleman, Mikhail Alidibirov, who is seen standing here in the mid-90s in front of what looks like a large water boiler, but it's actually our first experimental volcano. Now we do it like this. This is the modern inheritance, if you will, of those early experiments with Mikhail. And you can see here big stainless steel tanks. Below them, you can't see it too well here, but there is a high pressure, high temperature autoclave. You can see it glowing red hot. So we're doing experiments here where we place magma where my cursor is at this glowing red hot center of the autoclave. We bring it to the conditions that it is in the mountain at about 1,000 degrees Celsius and perhaps up to 1,000 bars. And then we rapidly decompress it. We remove the mountain and see what this magma will do. And quite often, more often than not, we end up with this in place of our solid magma piece. We have a field of ash, which has been generated by the event that we just precipitated. So all we need to produce volcanic ash is rapid decompression of hot magmatic systems. And I've shown you this video last time. I'll show it to you one more time because it's so beautiful to look at very quickly if I can get my cursor to work. Here we go. And you can see the decompression front hitting the top of the sample. Up is to the left. And you can see how the sample is literally torn apart simply by the decompression which has been sent into this chamber. And as I showed you last time as well, but I'll repeat it briefly for those who weren't there, into the tank comes the results of that process. First, a blast of the gas, which is holding it under pressure, and then pyroclastic ballistic thrust, which we can monitor here over a few microseconds with high-speed videos and get a lot of kinematic data and get a lot of kinetic data out of simply observing these flows over time. So this is truly experimental volcanology. This is trying to emulate, simulate the processes which are occurring in the volcano in the laboratory. So we get from this, for example, the first result, the answer, how much pressure, how much overpressure do I need? How much decompression must I instigate in order for this material to fail? And it turns out that it depends upon one property of the rock more than anything else, the porosity. If I have highly porous samples like pumice, then I only need about 3.5 megapascals, or about 35 bars, atmospheres, in order for that material to be destroyed by decompression. If I have almost no bubbles, I need 10 times that amount of fragmentation energy. Therefore, you can see that most of the material that's going to be destroyed in an eruption is going to be the materials that contains a lot of bubbles, and either it will come out as fragments of pumice, which still contain interior bubbles, or it will be fragmented even further down to the scale where there are no bubbles left because every single bubble wall is broken, and the result is glass shards, which we call volcanic ash. So these may seem like high pressures to you. I can promise you, for solid earth scientists, these seem like trivially small pressures, 35 up to 350 atmospheres. We also know how fast this takes place, and it takes place at a relatively slow speed. The acoustic speeds, the speed with which sound energy can pass through these materials in the unrelaxed state, is on the order of kilometers per second. All rocks on Earth have acoustic velocities of at least hundreds of meters, and if they are lithified into a solid state, generally kilometers per second, and they increase in velocity as you go down within the Earth. But the speeds that we're talking about here, where the decompression wave is driving through the sample, are much, much lower than those acoustic velocities. That means the sample gets the acoustic information that it is under tensile stress, and then it takes 10 to 100 times longer for it to disintegrate with the velocities that you see here. These velocities are obtained by measuring the dynamic pressure above the intact sample and measuring the dynamic pressure below the intact sample. The shock wave, or the decompression wave, the rarefaction front, which comes into the sample, is picked up by the first sensor. The material begins to erode by fragmentation, and when it reaches the second sensor, you get the second decompression of the second sensor. And the time difference between them very simply gives us the speed, the linear approximation to the speed of the propagation of the fragmentation front. So these things are grinding themselves to death. When we talk about volcanic explosions, you may think of a chemical explosion. We don't think that plays a big role. You may think of something which happens so fast that you can't observe it. What we're really seeing is eruptions which roll on for hours, days, or even weeks. And we believe the fact that they can roll on so long is because the supply of magma to the site of the explosion can keep pace with this slow erosion which we see through the physical fragmentation mechanism. A last picture from these fast experiments. We see here a specific energy as a function of what? As a function of the permeability, the speed with which gas can leave the material. And you see that there is no dependence of the energy density for fragmentation on permeability at low values of permeability, but as I drive to very high values of permeability, suddenly it runs away. Suddenly I can no longer talk about a specific energy density for a specific fragmentation behavior. And the reason that occurs is that simply the gas, which is under pressure in the pores of these rocks, is able to escape faster than the fragmentation front drives itself. Again, this slow fragmentation means that sometimes the gas gets out first, and if the gas gets out first, there's no need for the fragmentation because it has decompressed by losing its extra gas at high pressure without having to actually take the rock with it. And I joke about this by saying you can view all volcanoes as continuously degassing centers of the Earth, where the volatiles are emerging from the Earth's interior. They operate in a way like industrial factories producing gas, but sometimes there is an accident in the factory and the volcano decides that it will take the mountain with it. And you have an explosion and the mountain literally disappears. Now we'll go through slowly. Slowly means we can measure a lot more things. Slowly actually occurs in nature. Recall that picture of the Chitan Dome. And here we go. We have, for example, a uniaxial press, which allows us to squeeze samples under very controlled conditions. Again, something that you would expect to see in an engineering department or material science department. We pop thermocouples into it, and we want to measure whether or not we can see the deformation. Here we see beautifully this barreling deformation of an unsupported sample at one bar. You can see the crystals in it. You can see the thermocouple, which is poking through here. You can see the size of the samples, quite substantial samples, about the size of my fist. And what you can also see is that the temperature increases as we increase the strain rate. So as we go to extremes of strain rate here, we actually start to drive ourselves into the regime of shear heating. And this is something which complicates the fragmentation and the explosion in these systems, because if we shear heat enough, we can avoid the glass transition. We can push the glass transition away from us by decreasing our viscosity through the temperature dependence of viscosity. So we fall back into a liquid behavior due to the fact that we're shearing ourselves and producing the frictional heat inside of the material, which we call shear heating. And these two effects overlap. You can see two lines here which cross. One of the lines corresponds to the fragmentation of the sample. This is the purple line. The other line corresponds to the onset of viscous heating, which will push us away from fragmentation. And this temperature range is approximately the temperature range where these domes are cooling as they're on top of the mountain. So there's a prodigious complexity, which is potential in the materials engineering of these volcanic systems. It's wonderful for us to be able to understand the intricacies of the system, but it's a great challenge to understanding the behavior of these systems in a sense of civil protection. I've shown you this last time. I won't say it again. Ash in the Earth system. We now leave the volcano. I've told you that we've done experiments using gas ash reactors, little devices that, well, not so little, a meter long, that we set up in laboratories in order to study what happens after we have the explosion, because that's when the Earth system is truly impacted. And here we have, for example, the surfaces of glasses which have been fragmented and which have been exposed to the coexisting gases which come out of volcanoes. And we can see laden on top of all of these samples. I hope you can appreciate that these are crystals which have precipitated of calcium sulfate. Okay, we call it anhydrite. If you add water, it's gypsum. And these calcium sulfate crystals, of course, are water soluble. If they go into groundwater, if they go into soil, if they go into deposits which are laid down and rained upon, they can have significant impact. We also produce plumes of calcium sulfate together with the plumes of ash particles made out of rock. I have mentioned briefly this topic, which is one which brings me together with Fabian in this IAS fellowship, which is, of course, one of the great interactions between the technosphere and volcanoes, is that of jet turbines. And these jet turbines are attacked in several ways, which I went through last time and won't repeat. But I'll just say one thing here again. The turbines are hotter than the volcanoes. So if you put volcanic ash from a volcano into a turbine, it will be hotter in the turbine than it was in the volcano. And you know, in the volcano, it was a magma. It was flowing. It was a liquid. And this is what happens. We end up with glassy deposits on the turbine blades of these engines. The transport and deposition, and this is where you can, of course, have as many spectacular pictures as you want, is something which is largely the business of modelers of dispersion, or dispersal, which are in close contact with meteorological scientists because they need to understand the atmospheric dynamics. And here you see another plume, which is coming off in a relatively concentrated manner. And here you can see a map of the density of deposits in contours as you move away from an eruption of Hekla here in southern Iceland. We can go out into the field and we can measure how much ash is lying there here you have the contours of it. And this, of course, we can use to infer something about how literally the wind was blowing on the day that that eruption occurred, even if it's thousands of years ago. And you have complexities in these ash dispersal systems that I've shown you last time, but I'll repeat it here. If anybody wasn't there, you've seen one here and the other here. These are ash aggregates which are falling underneath Eyjafjallajökull. I'll show it one more time. Here's the first, disintegrates upon impact. Here's the second, disintegrates upon impact. And this proves to you that there are geological phenomena. For example, the radius and density and mass of these particles coming down, which are completely erased when they fall into the geological record. And they will not be preserved in the geological record. So we have our hands full in order to parameterize these systems well enough to be able to say what they're likely to do in nature. I want to finish this section before last of what I want to say with the example here, which is the serendipitous result, which is, I'm sure, the most beautiful experience that I will have in my experimental career. And that is that in the course of doing experiments to understand the dynamics of the ash and the gas jets which come out of these experiments, we inadvertently saw a phenomenon that we were not looking for, but which is everywhere in nature, which is lightning discharges due to the fact that we have charged ash particles blowing out of this system. These are what we call near event lightning, and those are events which are dominated by the nature of this flow, its turbulence, its grain size distribution, and the distribution of charge upon that grain size distribution. They're relatively uninfluenced by meteorology. And it means that we can say something about the distribution of these ash particles, which in turn can help us to say something about the dispersal that we can expect of these ash particles in real time if we simply monitor the discharges of lightning which occur around active volcanoes. So something we saw, we weren't expecting to see, check it with nature, see that it is very, very similar, and end up with a new monitoring method for volcanoes. It's wonderful to work in an area where you can be surprised in a very positive and constructive way, and actually with the prepared mind, the concept I'm sure you're all familiar with, you're able to make a great deal out of it in terms of application and very pragmatic results. Let me go on to my last topic, which is here. It's the last word in the title, which is intervention, and I was struggling for a long time to decide whether I would put a question mark behind that word, but here you have it. These incredible diagrams, they look more spectacular than any cartoon or comic or anything that your children may be watching in the internet. They are various people's literal cartoons to try to understand what the distribution of liquid is in the upper crust to mid crust, what magma chambers look like, what thermal regimes they might have, what is the likely physical state of the material which is producing the cap, which is holding the magma into the magma chamber. And if you look at these diagrams, I'm pretty sure that your first impression is going to be anything is possible, because these diagrams show such a spectacular range of ideas about these magma chambers. You would not be very far off from the truth to say, I can come up with one more. What I'm trying to say here is due to the geological complexity of the crust of the Earth, and due to our relatively low resolution views of what the crust looks like, geophysics has decreasing resolution with depth. We have a great challenge to understand in detail the physical state of storage and the physical state of liberation of magma from the lower, middle, and even upper crust. And so this is one of the greatest challenges that we have to advance in a broad way our understanding of when magmas are likely to do what they're going to do. We have, however, one possibility which might allow us to change this game forever. And I referred to it last time, but I'll refer to it again now. And this is the idea that we have, by accident, actually gone into active magma chambers. It's happened in recent decades. There's several examples of it having happened. So literally a drill core has popped into a liquid magma. Now, this sounds like a terrifying prospect for all of you, I'm sure. what basically happens is because these drill cores are, because these drilling operations are fed by water or muds, there are many fluids which are water rich and which have a cooling function as well. And so you can literally cool and freeze what you're drilling into as you go down into the magma chamber. So you can actually drill through magma. Not necessarily. What you would surely be interested in trying to be able to do reliably is to drill close to magma, to get very close to a high enthalpy source, which can provide at least a tenfold efficiency over time of the amount of geothermal energy that you can pull out from a low temperature geothermal field. And so we're ramping up for the political support the idea of being able to drill into magma, to understand how we can avoid it if we need to. In other words, what does it look like as I'm approaching the magma? And therefore, how we can do reliable geothermal systems just above the magma chamber. But also at the same time, to use the opportunity that this technological advantage, which we can derive from it, might give us financially in order to go intentionally into the magma, to observe the state of the magma in situ, leave sensors in the magma, and perhaps even set up a field of drill cores and drill holes which have gone into the magma, such that we can play with the magma field, putting a signal in one part of the magma field and measuring what the response might be in another part. And I'm convinced from what I know from my life in science and what I've seen come and go for ideas and certainties that have been washed away by new observations, that we will see things in this rhyolitic magma body in Krafla, which we've chosen as a target, which we do not expect, and which will therefore advance our understanding of the state of magma in the crust. And that's ultimately what we need to have a handle on if we're going to be able to produce more reliable management schemes for living around volcanoes. So magma intervention, perhaps. Thank you very much.
Thanks so much for a very absorbing, fascinating talk, and I can absolutely see why you're so fascinated by this phenomenon. We're slightly up against time constraints, but I think, it may be that some people will have to leave, but I think we should allow others who have questions to remain and ask questions, as long as that's okay with you, Don.
Absolutely. Absolutely.
So I'm not going to delay things further with further observations. I'll go straight to, I see we've already got a question. If I can say to anybody who has a question, if you'd like to type it into the chat, that may be the most efficient way, or otherwise just type Q in the chat and we'll unmute you to ask your question. But we already have a question from Sandra Sham, which for efficiency, I will just read out to you, Don. And to everybody else. And Sandra says, I did archaeological work on abandoned sites on both sides of the Dead Sea. I'm interested in your take on the effects of volcanic activity there.
I don't know very much about the volcanic activity in the vicinity of the Jordan Valley and the Dead Sea itself. I do have colleagues in Jerusalem. There's a very famous gentleman there who works in the field of volcanology, and having asked him once where the most recent volcanism was in that area, he said, you have to go a couple kilometers into Jordan. So I suspect that there is significant volcanism. Perhaps somebody else listening to this talk knows much more about it. I really haven't focused geographically there. It must be well known.
Okay, whilst other people are thinking of their questions, can I dive in there and ask you one? And it's really about how good our predictions are now. I guess it's a trite point to make that every eruption is unique. How much are we able to actually predict eruptions now? And what's the state of the predictive science of volcanology and I guess seismology?
It's a very big question, and I'll try to keep the answer as concise as possible. You remember the diagram I showed you of the magnitudes of volcanic events. So we call them all eruptions, but of course we're dealing with very small things and very large things. You can imagine that predicting large ones and predicting small ones might deviate from each other methodologically considerably. For systems which erupt quite frequently, for example, Etna or Hawaii, we have the best chances of being able to make a prediction because we've seen it happen in the life of any given scientist dozens of times. And we have the records of all those eruptions, and increasingly we have the records of very good monitoring systems leading up to them. In systems such as Yellowstone or Toba, where we know it's very unlikely we will see a major event in our lifetime, we have a very great challenge to understand what the repetitive or consistent signal will be leading up to mega eruptions, to major eruptions, because we simply haven't seen one over the course of modern volcano monitoring. If you would sit down 10 people in the field of volcanology and ask them the question you just did, I predict that you would get answers that would range from about 20% or even 10% all the way up to 80%. It depends upon how they interpret precisely what you're asking. If you would say, I have an active volcano, I've been sitting on it for 5 years, I've seen 7 events, what is the likelihood of my being able to predict the 8th? Then you would get an answer near 80%. I've seen it happen. That answer happen. If you would ask somebody, what is the global possibility of predicting an eruption in southern Chile? You would get a much, much lower value because you're dealing with many objects and you're dealing with a relatively poorly, although improving, monitored part of the world. This sounds perhaps a bit abandoned of hope, but I always stress the parallel, as I did, I think, in the last talk that I gave here at Durham, that it's a little bit like medical research. If you ask the question, what is the percentage of surviving cancer? It depends. It depends upon what kind of cancer. It depends upon your behavior, your age, your genetics. It depends upon all of these things. And volcanoes also have a multitude of physical constraints, which you can really draw a parallel to in the sense of medical research. We have epidemiology of volcanoes. We have patterns of behavior. We have ages. And we have, of course, the very nature of the volcano itself, which would be some sort of analog to genetics. So I'm going to stop there because I'm getting long in the answer, but I hope I give you a flavor about how we think when we hear this question coming from non-volcanologists.
Thanks. And we have a question from my IAS colleague, Laszlo Polos, who would like to know, how do you see the relation between the experimental and the simulation-based theory building?
So it has been dominated by one direction of the flow of information or the process of informing. It has been the experiments that have informed the simulations, in my experience. That means that, at a time when I began this work, I would go to somebody doing simulations of volcanic eruptions, and I would say, look how precisely we can predict the viscosity, this all-important property for flowing liquids. Please put it in your model. And of course, in the beginning of my career, they would send me away again because the models didn't have the sophistication to cope with our beautiful parameterizations. Now the situation is flipped, and of course, they're crying out to us to improve things, which we can't do with the accelerating speed with which computer science is moving due to the power of computers. Experiments are improving on a linear scale in terms of the number of people working on them. So we are now in a situation where everything we produce will be immediately incorporated into the world's best simulations. And that is the arrow of information delivery which is occurring at this time. We do, of course, have people who do simulations and occasionally see things they can't explain and can come back to us and say, please do this experiment or please do the other. But it's relatively rare and it should be done much, much more.
One thing that struck me towards the latter part of your talk was those beautiful diagrams, those very dramatic diagrams that you were talking about, the visual representations of what's going on there. What sort of role do you see visual representations as playing in the science or in the communication of the science and the sort of wider communication to the public?
So the role of, for example, cross sections, slices into the earth, we call them cross sections, and the history of geoscience is a very controversial one, because in the beginning and also in the complex field-based observations of mapping today, of geoscience, there is a great deal of interpretation and interpolation required in order to make sense of incomplete data sets, of exposure, and so on and so forth. And so we have, most of us who are my age, have grown up in the field of geology, where we've been presented with spectacular cross sections which have involved a lot of interpretation and which are more akin to cartoons than factual spatial plotting of data points at depth. So we live in this world between trying to image these systems at depth with great precision and trying to draw pictures which convey the processes which we feel must be behind the, for example, the geophysical and the geochemical information of what's coming out. We're a little bit like chemical engineers without having the input variables. We only have the output variables. So this, of course, would make any chemical engineer throw up his hands and run away, or her hands and run away immediately, with and rightly so. But it's the world we live in. It's a very incomplete world, and it's a very, I would say, it's a very dangerous world when one draws what one has for a personal image of what the data must represent. Then you must view any drawn cross-section as the personal opinion of the person who drew it. I have a very famous plot on my wall behind glass that I rescued from destruction about 40 years ago. It was produced in the early 60s, and it shows the skin of the earth running from the continents under the oceans and over to the continents again. And it's completely wrong, because it was in the absence of substantial continental oceanic drilling. And so it believes that continental crust runs underneath the oceans. And I use it as a test in exams when students come into my room to terrorize them and take the thing down off the wall and say, what's wrong with this diagram? But I found out who drew it years later. It was a team of 4 or 5 people. And these people did what they could with the data they had, but there's always the hand of the artist in the kind of diagrams that you see. And that should be clearly understood by the public. As I mentioned, that we're building this new building in Munich for 200 million euros downtown, and they want us to bring geo information to the public. And we have to go beyond just showing them the pictures. We have to show them how we know what we know. That is the part that the public, that the educated public or culture needs to have in order to have a responsible, active voting right in our culture. Otherwise, we are lost. And so this is the challenge, to show them how you can say what you can say, so that they can have an appreciation of how accurately you might be able to say it.
Great, thanks. Questions are now coming in. We've got time for 1 or 2 more, I guess. Alan Drews has tried to sneak 2 in there. I'm afraid, Alan, I'm only going to allow you 1, and I'm going to select your second question there. Do you think the next generation of volcanologists will move to study volcanism on other planets and moons in the solar system, such as Saturn's moon Enceladus, instead of terrestrial volcanoes?
Certainly. I mean, we already are studying volcanism in all the ways that are available to us on other planets. But I take it that the question implies more field-based study, so the human presence on those bodies. If that is the case, one of the most important things that we will have to understand when we get to any other terrestrial body, and one of the most powerful messages that came from the Apollo missions to the moon, was volcanic in nature. So we've had flybys of Mercury within the lifetimes of everybody who's listening to this talk, which are completely revised our understanding about how much volcanism there is on Mercury. We had the drastic question of Venus. Do we have, is Venus alive as a planet? Is it not a dead planet? Do we have active and widespread volcanism? Do we have active and widespread lightning? And why are we getting these strange phosphorus speciation signals that were recently in the press? Mars. I was just talking to a gentleman the other day, and he was warning me about the unpublished results of the seismometers on Mars, which will be published within a month or so, talking about the depth of the crust, the molten core which is remaining there, and the possibility of active volcanism on Mars. Unquestionably, when we go to these places, and even if we do it through orbiters, volcanism will be a major part of what we will understand about these planets, and there will be differences. I hope there will be differences because we firmly expect there must be, based on the atmospheric conditions and based upon the lithospheric conditions.
Okay, and thank you. Then we have a question about AI and machine learning from Halim Kusumacha. Sorry, I got that pronunciation way off, I'm sure. But the question is, what roles do you see for machine learning in volcanology as opposed to other theoretical computational approaches?
Yeah, machine learning, AI, what I read there. I'm not an expert in either. If it's about what I would simply put in my layman's terms, pattern recognition and the recognition of relationships between patterns, it's already happening. It's widely attempted in volcano monitoring because there may be subtle combinations between signals in a very heterogeneous salad of signals that we get from volcanoes: earthquakes, gas emissions, deformation of the crust, changing the chemistry of groundwater. How these things expressed in fully different units and with different natures and different time scales, relaxation times, how do I bring them all together to understand the whole? So actually there's great hope in volcanology that artificial intelligence and machine learning may be able to bring us further and show us patterns that we otherwise would not observe because we're not built as a species for some reason to do it.
Great. And one final one from Claire Hallwell, who says, physicists have had to go to incredible extremes to continue to find the most interesting frontiers of what is known. Where are the extremes for new discovery in volcano science? What's the frontier for your experiments?
Yeah, very good question, Claire. I won't say that the frontiers of my experiments are necessarily the most interesting frontiers of all the volcanology, but I'm sure there's an overlap between the two. I mean, depth for us is a great challenge. How do we get improved resolution and how do we ground truth, in a misuse of the term, what we think we know about volcanic systems, which we infer with great sophistication using petrology, using geochemistry, and using geophysics at the surface, where we perform all these things to greater depth within the crust. This is surely a generational, if not a century challenge of how we're going to move forward. Of course, I've hinted at what I think is one of the most important things we can do, which is to move our behavior from that of ancient medical people to modern medical people, in that we invent surgery and go in and look at these things. If you think about what difference that makes between modern medicine and that which went before, I feel we're at the same threshold today in volcanology. If we truly can intersect these systems at depth, even if the first ones are shallow and small, we have to have some people in this field and some people in geoscience who are willing to imagine that in 25 years, 50 years, or even 75 years, we will have completely different possibilities at our disposal. We have to begin. And we have to also appreciate, from a purely pragmatic point of view, that if you go for a big budget item, that it usually expands the small budget items, which can follow in its wake and do even more science than would have been otherwise possible.
Great, that's a great note to finish on. I should just note that that question was actually from Fabian Wadsworth,
Okay.
who was parasitizing Claire Hallwell's Zoom link. Anyway, thank you very much. We are way over time, but as you can tell, lots of interest and lots of questions. It just remains for me to once again thank you very much for a fascinating and an intriguing lecture. And
you're welcome. And I look very much forward to
virtual hand claps all around. Thank you very much.
Look forward to seeing a lot more of Durham when the situation permits. Believe me.
Yeah, look forward to having you.